Hello, everyone. Yeah, shout out to everyone who did their contribution for reviewing of version A or version 1 of SUMA solvency protocol. As we are getting ready for reviewing of version B or version 2, it's very important to have a great understanding of KZG commitment scheme. And today we're going to be hosting Adria, who will guide us through a whole process and hands-on experience on KZG commitment scheme. So welcome, Adria, and the stage is yours.
Okay, thank you. Well, welcome everybody. Thank you all for coming. I'm Adrià Torralba. I'm a PhD student from Universitat Oberta de Catalunya in Barcelona, and I'm on my second year of the PhD. And my PhD is focused on blockchain and cryptography. And today I'm going to explain KZG commitments, and this is also known as the polynomial commitments. Okay. So this is the outline for the presentation. And well, first of all, I would like to introduce or to present the motivations about why commitments, why do we need commitments in the blockchain space in particular. Then presenting some preliminaries for the polynomial commitments. Then we are going to explain the protocol itself for this particular article. And then after that, we are going to run a hands-on over an instance, an actual example of an end-to-end run for this protocol. Okay, and I will ask the audience to help me in order to do that. I will explain how later on this presentation. And finally, well, since you are auditing SUMA from the PSC, and you should be aware of security issues, I will say a few words about the security issues that can arise when you implement this protocol in a bad way. Okay, so first of all, why do we need commitments? Well, if you are here, maybe you are interested also in zero knowledge. Okay, and this is a slide from Dan Bonnet's ZK Whiteboard session 2, where he explains that right now the modern way to build a snark is by the combination of a functional commitment scheme with a compatible interactive oracle proof. I cannot go deep into that. So today we will be focusing on a functional commitment scheme, and in particular a polynomial commitment scheme. That is an instance, a particular example of a commitment scheme. Another motivation to learn KZGs is also because proto-Dan sharding, also known as EAP 4844, will need from KZG in particular, and this is a screenshot from frequently for a frequently asked questions from Vitalik regarding proto-Dan sharding. And here says that, well, unfortunately, using anything other than KZG would make proto-Dan sharding roadmap much more difficult. And this is really interesting because this thing is shipping today. Actually, it is shipping in like less than 4 hours. So what a better time to learn KZG, okay? Well, joking aside, yeah, this is a couple of examples about why KZG is interesting, and this is the article of KZG. This is actually it is named polynomial commitments, but it is called Kate or KZG in honor to the first author, that is Kate. So this is I will refer to this as polynomial commitment or Kate commitment or KZG. This is the same, okay? And to put you everybody in context, this is an interactive system, okay, where we have a prover and a verifier, okay? And the prover tries to convince the verifier that she knows about something without, in this case, revealing this something, okay? So let's go and start with the preliminaries for polynomial commitments. And the goal of this article is to prove that the prover that we know a polynomial phi of x expressed like this on the standard basis over a finite field fp without revealing it, okay? In particular, we want to prove that we know an evaluation of this polynomial phi of x, okay? So let's present the setup for this whole session. Fp is the finite field of prime order P, where P is larger than 2 to the 2k, and k is the security parameter. This alone, this is a whole topic, really interesting, but in our case, what we are interested here is that P is large enough, is a prime number large enough, so our adversaries will be probabilistic polynomial time. This means that anybody trying to, well, or even the verifier trying to verify things will be allowed to run polynomial time only, and sometimes make guesses at random. Okay, this is probabilistic polynomial time, and this setup means that our P is large enough so our adversaries cannot break the system. Okay, so this is like one technicality of this setup. Moreover, we will consider G star with the product as a multiplicative group. Okay, we also consider G as the generator of F of the finite field and also the group, where the order of the group G star is P. What is a generator? Well, a generator is if we have a finite field Fp star that is 1, 2, 3, 4 all the way along until pi minus 1, G to the n is falls inside this set for every n in the naturals, okay? And moreover, with only G, we can generate every single number here, okay? So only with this J, sorry, only with this G, we can obtain all the numbers on the finite field, okay? And finally, we will consider the degree of the polynomial we want to commit to be at most t, and this t should be lower than p. Okay. Well, until here, everything is good. Well, what else do we need to know as preliminaries? We need to run two cryptographic assumptions. Okay. The first one is the hardness of the discrete logarithm, that informally says that if we are given a generator G of the G star group, then if we are given G to the X in the finite field, finding this X is hard. This means that this is computationally unfeasible to do that. So you cannot do that in a reasonable amount of time. The second crystallographic assumption we need to run is the strong Diffie-Hellman assumption, that again informally says that given a generator G of this G star group, and if we are given with G to the A and G to the B, where A and B are elements on the field, then G to the A and G to the B are indistinguishable from G to the AB. What does it mean? This means that in addition to the last cryptographic assumptions, if we are given with G to the A and G to the B, we cannot infer information about G to the AB. Okay, so we don't have any more information about G to the AB by having G to the A and G to the B. Okay. Now, recall, please. Our goal is to prove that we know an evaluation of a polynomial without revealing the polynomial, okay? But the question is how? I mean, how are we going to do that? Well, the answer to this is commitments, okay? And a commitment is an analogy to a real world envelope, okay? In the sense that we want two good properties from this. The first one is that a commitment is binding in the sense that once I commit a message, I cannot change my mind later. I'm bind to this commitment. Okay? And the second property is that a commitment is hiding in the sense that a commitment does not reveal the message until you decide to open it. So by default, the message is hide until I decide to open and reveal the message later on the protocol. So, well, with that, I would like to pause here and stop here and ask the audience if they have any question. If not, I can continue. I don't know if I have here the chat. Okay.
Yeah, Adrian, could you say a bit more about opening the word? I think the word open is something we're going to hear a lot from Enrico next week. So could you say just a bit more about what opening means?
Yeah, opening means that once you commit a message, by default, this is like you have to imagine the analogy of a real world envelope is really good because I think that it works pretty well. In the sense that if you put a message inside an envelope and you closed it, this is hide, okay, and you cannot see the message. But then later, you can decide to open this envelope and reveal the message, okay? The way you do that is by when you commit a message in this protocol, what at the end of the day, what you are doing is like sending actually an element from the finite field. And when you open that in this protocol, and we will see that, what you will do is to send another message that only works if it's paired like with the previous commitment you did. So I will explain that like shortly in the opening phase. So the protocol here of polynomial commitments has 4 steps or 4 phases. It has a setup phase, a commitment phase, an opening phase, and a verification phase. Okay. And then here I put a summary, a nice summary about the whole protocol. So the first step, the setup. In this step, we take K and T. Remember, K is the security parameter that ensures that our P is large enough so our adversaries cannot break our system, okay? And T is the degree, the maximum degree of the polynomial we allow to commit. And this T should be less than P, the order of the group. And with K and T, we compute 2 groups, G and GT, of prime order P with K bits of security, along with a pairing. But what is a pairing? Okay, I mean, I lied about the preliminaries. We need another thing. A pairing. Well, a pairing is an application E that takes 2 elements from G, G times G, and outputs an element from GT, such that this pairing is bilinear. This means that for every A and B in the group, we have that E evaluated to G to the A and G to the B is equivalent to G to the A, B, and G. This means that we can put this exponent here and move that on the first element, or we can put both of them on the other element, or even we can take that outside of the pairing altogether. Okay, this is the bilinearity of property of a pairing. And the second property we ask for a pairing is for this to be non-degenerate. Okay, this means that if we evaluate E to the generator of the group, this doesn't output the neutral of the group. In this case, we will consider 1. Okay, so a pairing is simply an application that takes two elements from the group G and outputs an element from the group GT. Okay, and it has two nice properties. That is bilinearity. This, at the end of the day, for our case, means that we can play with the exponents here as we like. And the second property is that E is non-degenerate. This means that E evaluated to the generator of the group is not 1. So we are on the setup phase, and well, we take K, the security parameter, T, the maximum degree of the polynomial well auto-commit, and we compute G and GT of prime order P with at least K bits of security, along with a pairing. And now we know what a pairing is. Great. And with that, now we ask a trusted party who picks alpha randomly as an element of the finite field. Okay, and this trusted party computes this thing here. These PP are the public parameters, and this is a tuple consisting of G to the alpha, G to the alpha square, G to the alpha T. Okay, and remember that thanks to the two cryptographic assumptions we are relying on here, the discrete logarithm and the strong Diffie-Hellman, we cannot infer, once we are given with G to the alpha, G to the alpha square, G to the alpha T, we cannot infer what alpha is. We only know G to the alpha, G to the alpha square as a whole thing, as a whole numbers on the field. Okay. After that, it is really, really important and crucial, vital, that this trusted party deletes alpha. And I will say more on that later. Okay. And with this, we send the public parameters PP to the prover and to the verifier. Okay. So far we have three actors. The prover wants to prove to the verifier that she knows a polynomial without revealing the polynomial to the verifier. Okay. And now we have also another actor that enables us with, helps us with computing public parameters for both the prover and the verifier. Okay. Is it clear so far? Because now it will get harder. Well, it seems that everything is clear. Recall, we want to prove, the prover wants to prove to the verifier that she knows a polynomial without revealing the polynomial. To do that, in the setup phase, we require for the computation of two groups, G and GT of prime order P, and a pairing.
Yeah, before you proceed, it looks like we have some question come in.
Is it necessary the same
is
order
she-
as G? Usually is the case, but I think that this is not required. But usually in this case is the same. Yeah, the subscript T is because ancient notation, I don't know how to say. On the literature you find this like this, and this is to differentiate between the group of the input group and the output group. But yeah, that's a good question, and I should have mentioned that. We should think of the entire polynomials who in turn represent an intercomputation. No. Here, you should think as the exponents here as elements in the field. These are numbers. Okay, so here, A and B are elements on G. Are only let's say are only numbers. Are 7, I don't know, 34. And with that, we will play with the polynomials because this is the setup. So now we are going to define the polynomial and we will play with it. So far, G, A, B, and here 1 are numbers, are elements on G, and G has the elements from 1 to P minus 1. Is that clear?
Yes.
Okay. Actually, until here, I only talk about polynomials when I defined phi of x. That's the only polynomial we saw so far. Okay. The rest of the things are elements from the field or from the group, are numbers, not polynomials. Okay. What actually, if you recall, I'm sorry for doing that. Maybe I can do that. A0, A1, A2, all the way along until AT, these are elements from the field. Okay. I thought I was referring to AB exponent in the pairing. Okay. A0, A1, A2, all the way along until AT, these are actual elements from the field, but this as a whole, this is an element of Fp of x. And when we put that like this way, we usually refer to the polynomial field that takes as coefficients elements on the finite field P. This is usually the way we do that. So with that, we are on the setup. Well, we are done with the setup, and we were here sending the public parameters to the prover and the verifier. And very important, we delete alpha. Okay, this is vital. This is crucial for this to be working good. Does the pairing property also hold for the multiplication? AG, BG is ABTG. Well, in this case, we are working with a multiplication. We are considering the multiplicative group. I don't know if I understand you correctly, but the thing is that G to the A stands for G times G times G times G 8 times, and G to the B the same for B. So you can put that also in the sum notation that is G times A or G times B, and we will see that exactly on the hands-on example. But in your example, AG BG is ABG. Yeah, it also holds. But in your comment, it you should be saying that it also holds for the sum, because if you put AG, this is G summed 8 times. This is G plus G plus G plus G 8 times. So this also holds for the sum, but here we are working on the multiplication, because on the paper is done like this. Okay. Thank you for all these comments and questions. They are really interesting and make sense. Okay, this is the first part of the protocol, the setup. Okay, and now we are going to work with the polynomials. The second phase is the commitment. In this phase, the prover wants to commit a polynomial, and to do that, she runs the commit with the public parameters and the polynomial of that she chooses, and then computes this commitment. Okay, and the commitment, we are going to define this as this C, that is G to the phi of alpha. Okay, and again, here G is an element of the field. Phi of x is a polynomial, but if we evaluate a polynomial at a given point, in this case alpha, this is an element of the field, right? And if we do G to the phi alpha, this is a field element, this is a field element, the result is a field element. Okay? This is the definition of the commitment, okay? That said, the article says, and now the question is, but how do I evaluate phi of alpha if we don't know alpha? Remember that alpha is only known by the trusted party. The prover and the verifier, they do not know alpha. They know G to the alpha, G to the alpha square, G to the alpha t, but they don't know alpha. So how do we evaluate that? Well, let's see, okay? Because recall that from the public parameters, G, we have G to the alpha square, all the way along until G to the alpha t, where t is the maximum degree of the polynomial we allow, okay? Now, our commitment C is defined as G to the phi alpha, right? And if we express that in the standard basis, we have that this is nothing else than G to the A0 plus A0 I1 times alpha plus A2 times alpha square plus AT alpha t, right? And we can rearrange that in this way. We can put G to the A0 times G alpha, because we take this G and alpha, and we elevate that to A1. Then we take G alpha square, and we elevate that to A2, all the way along until we have G to the alpha t, everything to the AT, okay? But now we don't have alpha, but we have the public parameters, and we have already this G to the alpha, this G to the alpha square, this G to the alpha t. So using this rearrangement and the public parameters, the prover is able to compute this commitment without knowing alpha, which is a really clever trick. So the prover computes this commitment and sends this G to the phi alpha to the verifier using the public parameters. Is it clear how the prover is doing that? And now the relation with a polynomial, because until this is the first time we are using polynomials in the operations. Until before that, the setup is done only with field elements. And it is also important to recall and to remark that this commitment is only a field element, is only a number. This is not, we are not committing a whole polynomial. We're committing to a number at the end of the day. Is it clear? If not, please type on chat or go ahead and ask directly using the microphone. Because now we are going to see the opening and the verification that these are the two, where these are more difficult than this step. Okay, if everything seems to be going good, let's move to the third step, which is the opening. Okay, and this is the step where I don't remember who asked that, but here we are revealing that we know information about the committed message without revealing the whole message. This is in the sense, and in the commitment phase, the verifier notes our commitment and he writes that on paper, let's say, and he records our commitments. Now, on the opening phase, the verifier asks to the prover to open, in this case, open means to evaluate the polynomial phi of x at usually random number I in the finite field. Okay? To do that, the prover knows a clever algebraic trick, okay, which is the following. If we define y as the evaluation of phi at this point I, remember, phi of x is our polynomial, and now we are asked by the verifier to reveal, to prove that we know the evaluation of phi of x at this point I, that the verifier chooses. If we define y as phi of I, then observe that phi of x minus y has I as root. Is this clear? Because this is the basis for the opening phase. So if I have a polynomial phi of x and I have well, I've been given with an opening request I, and I evaluate as y the evaluation of phi of this point, then this new polynomial phi of x minus y has I as the root. Okay, and this is if you want, this is a consequence from the fundamental theorem of algebra, and this is equivalent to say that x minus I perfectly divides this new polynomial phi of x minus minus y. Okay, this in turns, what does it mean to perfectly divide? This means that if we take phi of x minus y and we divide that by x minus I, we have another new polynomial without a residue in the division, in the quotient. Okay, so this means that there exists another polynomial in the same field such that phi of x minus phi of I, this is this new polynomial here, is equal to this polynomial quotient times the thing for what we divided to. Okay, and this will be really interesting and important here. So, this phi of I is simply this polynomial here divided by this polynomial here. Okay, if you want, from this expression, if we take that and if we take that and we put that on the other side of the equal, we have that psi of I is equal to phi of x minus phi of I divided by x minus I. And we don't have here a residue. This is like a whole division. So finally, if we rearrange this expression here, the asterisk expression, we can obtain this expression. This new expression for our committed polynomial. Phi of x, this is our committed polynomial, is psi of x times x minus I plus phi of I. Okay, and this is simply take this element here and put that on the other side of the equal. So the verifier can come up with this expression. Now, we will define psi of x, our proof polynomial or quotient polynomial or whatever you want to call it. So we are going to commit this polynomial as the proof of the opening, just as before. We define C of psi as G evaluated to as G to the psi of alpha. Okay, and the way we do that is exactly the same as we did the first commitment. If you remember, we are using the public parameters from the trusted party, and if we rearrange the coefficients of this, we can take advantage of that, and we can compute this number here without knowing what alpha is. How do we know in advance that I is going to be a root of px? We don't know. We are building that. You don't know, you obviously don't know that phi of x. You can be sure that phi of x alone has I as root. But if I take phi of x and I subtract phi of I, the evaluation of this polynomial at I can be sure that I is a root of this. I don't know if it is clear, but for instance, can you see that, no? For instance, if I want to this is our polynomial. Okay, is it clear?
Yes, it's good. Thank you.
Okay, because this is a spoiler, because we are going to do that later. So far, we have, well, the prover has come up with this clever trick to prove to the verifier that she knows the polynomial without revealing the polynomial. Okay. Now, at the end of the third phase, that is the opening, the prover sends I, the requested opening, along with phi of I the image of this and the commitment for this proof polynomial or this quotient polynomial. However you want to call it. And finally, it comes the verification, okay? Now the works is for the verifier, okay? The verifier has to verify that phi of I is indeed the evaluation of the committed polynomial C at I, okay? The C is the original commitment, the committed polynomial. To do that, B has these tools. B knows the original commitment, C, that is G to the phi alpha. He knows I, obviously, because he chooses that. He knows phi of I, because the prover provided that. And he knows this commitment, this new commitment for the proof polynomial, that is G to the psi alpha, okay, that the prover has compute. Now, recall that we can come up with this expression from this trick, okay? So the verifier now knows an expression, an alternative expression for the committed polynomial. Phi of x is psi of x times x minus I plus phi of I, okay? And this identity also holds for alpha, because this identity is for every element on the field, but in particular, alpha is in an element of the field, so it also holds for alpha. Okay, so if we replace x by alpha, this is still valid and correct. So B would like to compute something like G to the left-hand side equal to the G to the right-hand side. Why? Because he knows some things here. For instance, he knows this, and he knows G to the phi I, okay? But we don't know G to the alpha times this. So how can we do that? Because this seems a good idea, but to do that, B needs to know alpha, and alpha is known by only the trusted party, and at the end of the setup phase, nobody knows alpha, not even the trusted party. Well, in that case, this seems like a good idea, but we might need to know alpha to do that. Well, the answer is obviously no, because here is where pairings come to the rescue, okay? In the pairing verification, B should check this thing here. And why this thing here? Because this is a convenient way to check this verification by doing only 3 pairings. This pairing here, this pairing here, this pairing here, and a multiplication, okay? The reason and the derivation from the last one, from this thing here to here, is explained on the paper, but I don't have enough time to explain that. So our goal here is to check, the verifier wants to check that this left-hand side is equal to this right-hand side. And we are going to prove here that these two are equal. And to do that, we are going to take advantage of the useful properties of the pairing that we explained, that we saw before. In particular, if we take the right-hand side, the right-hand side is this, and this is equivalent to, we replace C of psi. This is G to the psi of alpha. This is this element, G psi of alpha. And remember that we can play with the exponents as we want. So we take the exponents from the right element and we put all together on the left element. Okay, and we maintain this element here just like this. We don't touch that. Now we are here, And this is equivalent to taking this thing outside of this, and we can multiply the same basis, EGG to this thing times EGG to this thing, and we can put that together here. And if you remember, this is the expression exactly of phi of alpha, because phi of alpha, well, phi of x decomposes as psi of x times x minus I plus phi of I. And now we can put that back here inside. This is g to the phi alpha. And if you remember, g to the phi alpha is simply this commitment C. So with the right-hand side and these derivations, we obtain the left-hand side. So we are happy and we check that this is okay. Now, the summary of all this protocol. I know that this is a lot, but I hope that this will help. In this protocol, we have 3 actors. We have a trusted party, a prover, and a verifier. Okay? And we have 4 phases. The first phase, the trusted party generates alpha randomly on the field and computes the public parameters for both the prover and the verifier, and deletes alpha. This is very, very important that the trusted party deletes alpha, so nobody, not the prover, not the verifier, not even the trusted party, knows alpha. Once the trusted party computes g to the alpha all the way along until to g to the alpha t, it is really, really important that this alpha is deleted. Okay, this cannot be leaked. Once this trusted party is done, he sends the public parameters to both the prover and the verifier. Okay, and this is the end of phase 1, the setup. Now, the prover wants to commit a polynomial. So she picks a polynomial with coefficients on the finite field, and she computes this commitment using, sorry, this is x, this should be alpha. Sorry for that. This computes, she computes the commitment, and this commitment is only an element of the field. And she is able to do that without knowing alpha because she knows the public parameters. So the prover sends the commitment to the verifier. This is the commitment phase. Now the verifier says, okay, this commitment is cool, but now I want you to open the polynomial at some random point I in the finite field. So the verifier sends I to the prover. The prover takes I, and she says, okay, I will compute this quotient polynomial using the trick that we saw, and we are going to compute the a new commitment for this quotient polynomial. Okay, and we are also going to evaluate phi at I, the requested point, and the prover sends I, phi of I, and this new commitment to the verifier. Finally, the verifier needs to check this quality by computing 3 pairings: this pairing, this pairing, and this pairing, and this multiplication. And well, how is it going so far? Because now it is your turn. Okay, and the idea is, well, first of all, if you have any questions, any doubts, anything you want me to try to clarify, please go ahead. And if not, we are going to start with the hands-on part of this workshop. So I suppose that everything is clear.
Yeah, I guess we can start with the hands-on.
Yeah.
There's a question. How does the pairing function work?
How does the pairing function work? In what sense? What do you mean? A pairing is simply an application, okay? This is an application like f of x is x squared, but instead of x squared, it's another function that is bilinear, okay? And now we are going to see a bilinear function as a pairing in this workshop. Just to make sure to compute A is alpha minus I, because we don't know I, we compute exactly, yeah, inverse of G to the I. We are going to see that just right now. I got that disconnected. Okay, you should be seeing this now. We're going to do that full screen. And well, if you remember, we have three actors: a trusted party, a prover, and a verifier. Okay, now the idea is that I will set up some parameters, and we are going to do an end-to-end run of this protocol, okay, going through all the 4 phases. To do that, the idea is that I will need 3 volunteers from the audience: a trusted party, a prover, and a verifier, and I will moderate and help with if they need with that. Okay, so first of all, I need a trusted party. Who wants to be a trusted party to compute this? To compute the trusted setup and these kind of things.
Trusted setup, raise your hand.
Sorry again, please. Me too. Okay.
Uh,
Then I have 2 volunteers, 3 volunteers. Perfect. Okay. Tida, the B. I can be. You're going to be the trusted party. Okay. So in this phase, I'm going to set up this for you. Until now, we've been working with with the group with the multiplication, but now we are going to do that with the sum. Okay, so we are going to define this as F11 with a sum where P is 11, T is 2, and G is 2. Okay, here actually any element different from 0 generates. This is I'm sorry, I have like pretty shit letter, but I will do my best. I will do my best. We will be working on F module 11. This means that we have 0, 1, 2, 3 all the way along until 10. When we get 11, we start again at 0. Okay, so our prime number is 11. T is 2. This means that the maximum degree of the polynomial we are allowed to commit is at most 2. And we have G equals 2 as the generator. Now, we're going to define, well, I'm going to define the pairing as this. The pairing will be E of X, Y is equal to x times y mod 11. Okay, and for instance, this is the person who asked what does the pairing function work. This is an example of a pairing function. And why is this a pairing function? Well, let's see the two properties that we ask for a pairing. If you recall, we ask for a pairing to be bilinear. This means that if we do e x1 plus x2 times y, this is equal to, the definition says that I have to multiply x by y, so I take x1 plus x2 times y, x1 plus x2 times y. I apply the distributive property. This is the same as x1 times y plus x2 plus y. And I realize that this is e x1 y plus e x2 y. So check. We also need to compute to check this the other way around with y. But I hope that you can see that this is the same. Well, this is equivalent, and we can obtain this same result. So the first property holds. Is it necessary for pairings to hold distributive property over addition? Yeah. Actually, this is provided by the fact that you are working. If you remember, a pairing is an application that takes two elements from G and outputs an element of GT. Okay, and this G has already the distributive property over the addition. Okay, this is by the definition of a group. Because if you don't have this property, you cannot call this a group. So this is why we have this property already. But good question. So we have like half a pairing because we have two requirements and we already set up one. Now, the second requirement is that this is non-degenerate. Okay? If you remember, this requires to be that E evaluated to GG is not, in this case, 0, because it's the neutral of the sum. In our case, E G is 2, so E 2 is, by the definition of the pairing, 2 times 2, which is 4, which is not 0 mod 11. So great, we have a pairing. Okay. Any questions so far? Is it clear? Well, if it is clear, then we are going to proceed with the trusted party setup. Okay, remember that the trusted party needs all of this setup here, and a pairing, well, needs to set up this, and we want to output public parameters. Okay, so I will define that alpha is 3. So now the trusted party here needs to compute the public parameters that I will write this for you. P is G alpha square G. Why alpha and alpha square? Because T is 2. So we are going to allow to commit polynomials with degree at most 2. Now, Tedaf, it's your turn. How are we going to do that?
What do you? So I just multiply alpha by g.
Okay. Well, first of all, the first element is g, and g we have that already, right? G is 2.
Yeah, g is 2. Yeah.
Perfect. We have
So I
done.
do-
We have one.
So first is 2. The second one is 3 times 2 mod 11. So
Okay. Okay. And the second one, and sorry, and the third one.
And the third one is 3 to the 3 squared, so 9 times 2 mod 11, so it's 8.
Okay.
No, the 9
So-
times 2, so it's 7.
Okay, perfect. So we have the first element is 2. The second element is 3 times 2 is 6. Mod 11 is 6. And the third element is 18. Mod 11 is 7. Perfect. So this is G, this is alpha G, and this is alpha square G. Perfect. So we have the public parameters, and we send that to both the prover and the verifier. Cool. Is your job done here?
And I need to make sure I delete alpha.
Perfect. So I will go ahead and we delete alpha. Nobody knows what alpha is. That's great. That's really great. That's really great. Good job. Now, so I will write here public parameters are 2, 6, 7, which this is G, this is alpha G, this is alpha square G. By the way, can you see that like reasonably well, or do I need to make it larger, or it is good like this?
It's okay.
Okay, perfect. That's great. So now we're going to commit. This was the setup. The commitment phase. Now I need a prover that will commit this polynomial. Phi of x is 3x squared plus 5x plus 7. Okay? So who wants to be the prover? That's what we just decided for this process. Okay. I'm lost here.
Yeah, there was a question about.
Okay.
Okay.
Yeah. This is what I said about the multiplicative notation and the addition notation. If we work with G and the multiplication, your operation multiplies. So when I want to, I have a generator, okay, and when I want to multiply G times A, this is, I mean, G by some element A, I elevate that because my operation, imagine I have, my operation is a multiplication, but the symbol is op. So I will be doing that G op, G op, G op, G 8 times, okay? And if my operation is a multiplication, this operation is this is G times G times G times G 8 times, which is the same as G to the A, okay? But if my operation is sum, this is G plus G plus G plus G 8 times, which is AG or GA, because the commutativity also holds here. Is it clear now? Okay, perfect. So this is unrelated to our thing. So now we need a prover that he's going or she's going to commit this polynomial. Okay. So I had another volunteer. I can be QPJM. You are the prover. Now, what are we doing here?
The equation, the calculation is a little bit long, so I will put it in the chat.
No, don't worry. No. Just tell me. Just tell me. I will write. I mean, you say and I write. Okay. I will go ahead, and this is the polynomial you want to commit, and our commitment is C. Okay. That usually, if you will find in the literature that we need to evaluate this. Okay. When we put this element here in these square brackets here, this means that we evaluate this element in the field. Okay. And what does it mean? It means that this alpha square could be alpha, well, this element, this sorry, alpha square, no, this x square will be alpha square g, this x will be alpha g, and this one here, because we have this will be g. So the thing we need to compute is, as you said, this is very long. This will be 3 times alpha square g plus 5 times alpha g plus 7g. And don't worry, because you have g here, alpha g is here, and alpha square g is here. So can you say what I will be what I need to write here?
3 times 7.
Okay.
Plus 5 times 6.
Perfect.
Plus 7 times 2.
Okay. And if you do the math, this is 65. Okay.
Yeah.
Which is 10 mod 11.
Yeah, 10. Yeah.
Okay. So our commitment is 10. If you remember, I always said the commitment is an element of the field, is a number. We are committing a polynomial, but we are representing this polynomial as a number only. We only commit a number. So now the verifier knows that we send that to the verifier. Okay. The verifier notes, okay, this polynomial, this prover has commit to 10. Cool, perfect. Now, don't worry because, well, don't worry. I would need soon a verifier, but for now, let's say that the third person Y5 Yash will be the verifier, and the verifier asks you, the prover, to open at I is equal to 1. Okay, and I have 3. Okay, it's 3, or it should be fixed 7g, so it is 10. Okay, perfect. Yeah, we have the commitment is 10. Now the verifier asks you, the prover, to open the polynomial at y sorry, at I equal 1. Now, prover, what do you need to provide to the verifier? I recall you that you need to provide with with I, phi of I, and this commitment of C to the verifier. Okay? And what do we have? What do we have here already?
I is one.
You know I already because the verifier asked you to open at I equal 1. This is 1. Okay, we can easily compute that, right?
Yeah, it is 4.
It is 4. Let me check. Correct, this is 4. Phi of I is 4. It is 4 mod 11. Perfect. And now we need to compute this psi of x. Okay, and I recall you that this psi of x has this expression. This is phi of x minus phi of 1 divided by x minus 1. Okay, so our polynomial was 3x squared plus 5x plus 7, right? So with this information on the screen, you should be able to tell me what I should put in the numerator and the denominator. So please go ahead.
In the numerator,
Yeah.
3 times x squared plus 5 times x plus 3.
Okay. Plus 3. Plus 3. Why? Because it's plus 7 minus 4.
4, yeah.
Okay. This is 3. And the denominator?
X minus 1.
Perfect. Okay, so now we are going to divide this polynomial on the numerator by this polynomial on the denominator. And if we do, and if we did that well, we should be obtaining a polynomial without a residue, without a remainder. Okay, so I don't know how you divide polynomials, but I do like old school. And well, what are we going to do now? What is the result of this? I mean, this is something that most people usually forgot about that because this is not that used. But usually I put here the amount I need to have this when I multiply this number here by this number here. In this case is 3x. Okay, so 3x times x is 3x squared, and I put here with a sign change. So I have 3x squared, and 3x times minus 1 is minus 3x, but I have to change the sign, so it's plus 3x. This is eliminated, and then I sum exact 8x plus 3. Do you follow me?
Yeah.
Okay, and now the same for this thing. What I have to put here in a way that if I multiply this thing here by this thing here, I eliminate this thing here.
Plus 8.
Plus 8, correct. So 8x, I put here minus, and 8 times minus 1 is minus 8, and I change the sign, plus 8. So I eliminate that, and 3 plus 8 is 11, but 11 mod 11 is 0. So great. we have our proof polynomial or quotient polynomial. So phi of x is 3x plus 8. And I mean, is it clear until now?
Yes.
Do we take while doing? If we use 15 in case, yeah, but if we use 15 instead, then remainder would be 0 by default. Yeah, the thing is that I don't know if panic error are you're referring to use a finite field of where the modulus is 15, but this won't work because in order to have a field when you have this modulus, the module needs to be a prime, and 15 is not a prime. This is why we choose 7, 5, 11, 13, and these numbers. So again, is it clear what we done? We are trying to provide with the verifier with I, we have already phi of I, which is 4, and we need a commitment for this polynomial that we compute, right? And well, we are going to do the commitment just as before. I will write this for you. This is 3 times alpha g plus 8 times g. And I recall you that the public parameters are 2, the second one is 6 and 7, and this is g, alpha square g. So now, prover, what do I need to write here?
3 times 6 plus 8 times 2.
Sorry again?
3 times 6 plus 8 times 2.
Okay, that's
Yeah,
great.
and it is 1.
And this is 34, which is 1 mod 11. So our commitment is 1. So in this step, the prover sends to the verifier 1, 4, 1. Okay, and this is I, this is phi of I, and this is the commitment of C. Right? Everything is clear so far? If everything is clear, we are going to go to the last part of the protocol, in which the verifier needs to verify all these things. Okay? So verification to the verifier. I recall you that you have these tools. You have that the commitment original is 10, that I is 1, that phi of I is 4, and that the commitment for the second polynomial, the proof polynomial or the quotient polynomial, is 1. Okay, you have these tools. I also recall you for convenience that G is 2, that the public parameters are 2, 6, 7, and this is G, this is alpha G, this is alpha square G. Okay, and that the pairing is EXY is X times Y mod 11. This is the information we have so far. Okay, and I recall you also that you need to check this pairing. Well, this identity of pairings. Okay. E of C plus minus phi of I is equal to E of this commitment and here I compressed the last expression that we prove on the presentation to these two pairings. Okay, so if we find that the left hand side is equal to the right hand side, the verifier accepts the proof. Okay, and I recall you that this is the same as G to 1 that we saw in the presentation, and this is the same as G to alpha minus I. Okay? So let's start with the left-hand side. Who was the verifier? I think.
Yeah, so
Okay, cool.
yeah, so for LHS, we have in place of C, we'll write 10 and minus phi of I, we'll write it as 4. Will we write it as G raised to?
Okay,
No,
wait. Wait. I will copy the left-hand side, the number 1 here, and this is the commitment plus minus phi of I and 1. Okay? The first thing here is to notice that we don't have everything on the with a positive sign. We have one negative sign here. So we need to get rid of that. This means that minus phi of I is minus 4 because phi of I is 4 here. And minus 4, what is modulus 11?
7.
7, correct. Okay, so we are going to replace that here. So with this, we have the pairing is the commitment plus 7 evaluated, comma 1. Okay, and well, this thing here, I recall you that this is the same as 7 times G, and this is the same as 1 times G. So we're going to compute that. Okay.
So 7
What
times
is
G
it?
will give us 3. Yeah, 7 times 2 will be 14, and then that will like 14 mod 11 will be 3.
Okay,
And 1
but
G will be 2.
don't worry about the mod until the end. I mean, first compute all the things inside this here and here. Then we forget about the modulus. The modulus we're going to do at the end of the expression. Okay, so first we're going to compute that, sum that, compute that, then apply this by this definition here, and then at the end we're going to do the modulus. Okay, because it's easier. So with this, we have that this is E of the C is 10. 10 plus, as you said, 7 times 2 is 14, right?
Yeah.
Comma, 1 times G is 2. So 2. Then this is E of 24, 2, right?
Yeah.
And our definition of the pairing is E of x and y is x times y. So this is, how much
48
is
mod.
this? 48, correct. And this mod 11, how much is this?
4.
4, perfect. That's great. So the left-hand side is 4. And let's see if the right-hand side is as well 4. If it is, then the verifier checks the proof and believes the prover. Okay, I need to scroll down and well, so I think I will, because I don't want to write it again. Okay. Now, number two. Number two is this pairing here is E of C of C, comma, alpha minus E, which again, we have a negative sign here, right? We need to get rid of this. Now, minus I is -1, right? Do you agree with me?
Yeah, equal to
Okay.
10.
Perfect. It is equal to 10 mod 11. So we are going to replace minus I with 10. That's right?
Yeah.
Okay, that's cool. So, alpha plus 10. And now, what do we have here? Because I recall you that this is G alpha, and this is 10 times G. And this is 1. This is this thing here. Okay? So we're going to, if you want, replace all these things, and we're trying to compute this pairing. So we have E of
1.
1, comma,
6
what we
plus
have? 6 plus
20.
20. That's correct. And this is 1, 6 plus 20 is 26. And by the definition of the pairing, E of x, y is x times y. No? So what is this result?
26 mod 11. Yeah, which is 4.
This is 4. Mod 11. Well, since the left-hand side is 4 and the right-hand side is 4, the verifier accepts the proof, basically. So it says, great. And everybody's happy. Okay, questions so far? Comments, remarks? Because if not, we are almost done. Because if you remember, it was dangerous to have, well, it is dangerous to maintain a copy of alpha, okay, if you remember. So regarding the security issues, what happens if alpha is leaked, okay? Well, the problem is that if alpha is leaked, then P can create false proofs that B will accept, which is very, very bad, okay? And let's see how we're going to do that. Well, we have our polynomial here. P1 is 3x squared plus 5x plus 7, okay? And if we recall, alpha was 3, okay? What happens if the prover knows somehow that alpha was 3? Then the prover can commit to this, okay? And in particular, he can evaluate P1 of alpha because he knows alpha now, okay? And P1 of alpha if is 43. We don't even care about modulus here. And then he can come up with another polynomial, for instance, this one. Okay, this is the polynomial committed at the beginning, and this is the commitment. The commitment is g to the 43, okay, for P1. But if you evaluate P2 at alpha, is also 43. So it has the same commitment. So we have that the commitment for P1 is g to the 43, which is also the commitment for P2, which breaks the binding property. Okay, so in order to solve that, or to solve or to mitigate or to secure these things, I would use multi-party computation to compute alpha. And this is what I write here. Okay, if P somehow knows that alpha is 3, then this is the polynomial we have committed. Then P of 3 is 43. This is the second polynomial I showed you. P2 of 3 is also 43. So the commitment for P1 is G to this number, is G to 43, which is the same as the other commitment. And it breaks the binding property. So use multi-party computation to generate alpha. Okay? So, well, that's more or less all from my side. Thank you for your attention and thank you for staying till the end of this workshop. If you have any question, doubts, want me to clarify something, please go ahead. Thank you.
Yeah, thank you, Adrian. Let's see if there are any questions. Otherwise, we can wrap it up.
Okay.
Thanks, Andrea. This was great. I expect fellows will have more questions as they digest this. So I hope you can join us on Discord and have more conversation there. So
Okay,
this was great.
perfect.
Thank you.
Okay, thank you. I've already joined your Discord. Igor invite me, so yeah, I will be around. If you can think that you will, well, you have recorded that, so you can review that, and yeah, you can ask me questions later for sure.
Yeah, I guess fellows will be pinging you since we're gonna be diving into version 2 of Summa that is using KZG
Okay,
internally.
perfect. Okay, perfect.
So yeah.
Cool. That's great.
All right. Thank you.
Thank you for
everyone.
having
Thank
me.
you, Adria.
Thank you.
Yeah, we stay in touch.
Thank you.
Okay,
Bye-bye.
perfect. Bye.
Bye bye.